In this example, we're going to solve an equation containing multiple logarithmic expressions. What we're going to want to do is what we've done with simpler equations, which is to use the property that when we have log base a of x, and that's equal to y, we know that that's true if and only if we have a raised to the y equal to x. So in short, we can convert that logarithmic equation into an exponential one. In this particular case, though, we have multiple logarithmic expressions, and we have a difference of two of them. So as we're looking at this, we see that we have log base 7 of the quantity x minus 1 minus log base 7 of the quantity x plus 5. So we'll first need to use other properties of logarithms before we can continue solving this equation. And the key property we're going to use here is that anytime we have log base a of m and we subtract log base a of n, then that's equal to log base a of the quotient of m and n. So we'll use these properties here. We have log base 7 of x minus 1, and we're subtracting log base 7 of x plus 5, and that whole thing is equal to negative 1. So first thing we'll do, we'll apply that property of logarithms. So this becomes then log base 7 of x minus 1 divided by x plus 5, still equal to negative 1. All right, so at this point we have a single logarithmic expression, so we can convert this to exponential form. So instead of having log base 7, we're now going to have an exponential expression with base 7, but it'll be 7 to the negative 1, now equal to x minus 5 over x plus 1. And at this point, 7 to the negative 1, we'll want to note that that's just the number 1/7. So we've got 1/7 equal to x minus 1 over x plus 5. So at this point, we have a rational equation. So what we want to do to solve it, multiply each side by the lowest common denominator we see of those rational expressions. So from here, we'll multiply each side by 7 and each side by x plus 5. And what that should do then is clear out all of those denominators. And what that will do then is clear out all of those denominators that we have. Put in 7 and x plus 5 over here. Okay, so the equation we're left with then is that x plus 5 is equal to x minus 1 times 7. So we'll have x plus 5 equal to 7x minus 7. And that's just a linear equation, so as we solve that, we'll have 5 equal to 6x minus 7, subtracting x from each side, and then adding 7 to each side. We'll see that 12 is equal to 6x, which means that 2 is equal to x. And as we go through, we'll do a quick check. It's important when we solve equations containing logarithms to include the check and the solution set because there's a potential for extraneous solutions. So we'll make sure we put this check in. So we'll check if log base 7 of 2 minus 1 minus log base 7 of 2 plus 5, we'll check if that's equal to negative 1. And what I'm really checking when I'm checking for an extraneous solution is that all of these expressions within this equation are defined, which they are. To check that I didn't make an error, I'll make sure that each side is equivalent. So continuing here, we'll have log base 7 of 1 minus log base 7 of 7. And we're again asking ourselves, does that equal negative 1? Log base 7 of 1 by our properties logarithms is just 0. And log base 7 of 7 is 1. So indeed, 0 minus 1 is equal to negative 1. So that checks. And then as our last step, we'll state our solution set, which will then just contain the number